All right. Well, welcome everybody to Cheg's live calculus office hour. It has been about a month since we've been together. We were together back in December, took a break for the winter, and now with the new semester starting, we're excited to get started with you. So a big hello to everyone who's rolling in right now. Welcome to our live office hour. This office hour specifically is going to be for calculus, brought to you by Cheg. I'm at Wallace. You probably know me from Instagram, TikTok, or YouTube, or my other channels where I post out memes. Come for the memes, but stay for the math. I find a lot of humor and excitement in math and hope I can share that with you. For those of you who have joined our live events before, welcome back to a new semester. For those of you that are here for the first time, the goal here today is to help you understand your calculus course and concepts better. I'm going to be here each week, every Tuesday at 5:15 Pacific time, 8:15 Eastern time to do just that. This is your virtual office hour. I'm here to help. So if you have any questions, don't be shy. Make sure you're sticking them in the chat, and I'm going to try to answer as many questions as you can submit. So to kick things off, let's start taking a look at what I'm working on right now in my calculus class, and that's going to be partial fractions. So let's do an integral of partial fractions. We're going to find the antiderivative of x minus 9 over x squared plus 3x minus 10 dx. And with partial fractions, we want to take this fraction and we want to break it up into pieces that are easier to integrate and easier to handle. So the way we're going to do that is we're going to first factor this denominator. So we have to figure out what's going to factor to x squared plus 3x minus 10. Well, x squared is x times x, and 10 is 5 times 2. To get them to add to 3, we're going to have a positive 5 and a negative 2. So we're going to split this fraction up so that it's something over the x plus 5 plus something else over the x minus 2. And we want this to be exactly the same as our original fraction, the x minus 9 over x squared plus 3x minus 10. Well, we're going to solve this equation by multiplying through by the least common denominator, and that's going to give us something we can solve. So when we multiply, we're going to end up with a times the x minus 2. Oops, that's not a 2. That was a 3. I don't know where that came from. A times x minus 2. Then we've got plus b times the x plus 5. And that's going to equal this x minus 9 as the entire denominator reduces out. What's really nice about this equation is this equation is going to be true regardless of what x is equal to. So I can pick any convenient value for x. For example, if x was negative 5, this would all go to 0. So let's look at what happens when x is negative 5. Negative 5 minus 2 is negative 7 times a equals, because this term went to 0, negative 5 minus 9 is negative 14. Dividing by 7, I now know that a is equal to 2. We've got our a, still need to find our b, and we'll do that with much the same strategy, because if x is equal to 2, 2 minus 2 is 0, and this term's going to go away. So if x is equal to 2, we get 2 plus 5 is 7. B equals 2 minus 9, which is negative 7. Divide both sides by 7. B is equal to a negative 1. So now we can rewrite our integral as another equivalent integral that's going to be easy to solve with the a of 2 over the x plus 5 plus b, which is negative 1, over the x minus 2. And what's nice about this integral is each term there is now very easy to solve and find the antiderivative of. The antiderivative of 2 over the stuff is 2 times the natural log of the stuff, x plus 5. Put a line here to keep that separate. Plus a negative 1 times the natural log of the x minus 2. And of course, we never forget the cheese. Add a plus c. And we've got our solution to our problem using partial fractions. So hopefully that was a helpful little review of partial fractions. Before we dive into the next question, let's pause for a second. If you're just joining us, welcome. I'm at Wallace here on behalf of Cheg to help you tackle some of your toughest calculus questions. I am here every week at this time, 5:15 Pacific time, 8:15 Eastern time. So if there's a question on your mind, drop it in the chat. So let us know what your questions are. I see a second theorem of calculus question coming in. Let's take a look at the second theorem, second part of the fundamental theorem of calculus. I think that's where the AP classes are right now, so that's just perfect. So hopefully you're in an AP calculus class. Second part of the fundamental theorem of calculus. Now here's the challenge I have. The fundamental theorem of calculus, part 1 and part 2 are not clearly defined which one's part 1 and part 2. Some books say this is part 1, some books say that is part 1. I'm going to guess part 2 is the one where we have the limits on top and bottom and we're going to plug those in. But just in case I'm wrong, we'll do one of both part 1 and part 2. So I think this is what you mean by a part 2 question. We're going to find the antiderivative, and we're going to integrate from maybe 0 to 3 of 5x to the 4th. Let's go from 0 to 1. Let's do 0 to 2. Make it a little more interesting, right? 5x to the 4th minus 2x dx. So according to the fundamental theorem of calculus, part 2, we're going to find this antiderivative like normal first, and then we can evaluate it at these limits to find the area between those 2 points. So the antiderivative, we can increase the exponent by 1. 4 goes up by 1 to 5, and then I divide by the new exponent. That's really nice. Those 5s reduce out. Minus x, increase the exponent by 1. And boy, that 2 also is going to divide out when we divide by 2. Now, normally we would at this point say plus c. But because this is a definite integral, we're going to say instead we're going to evaluate it from 0 to 2. The reason we don't do the plus c is when we plug the 2 in, we'll end up with a positive c. And when you plug the 0 in, you end up with a negative c. Plus c minus c, it goes away, so we don't worry about it if we have limits to our integration. So now I can plug the 2 into the x's. So we end up with 2 to the 5th minus 2 squared. And then we're going to subtract what we get when we plug the 0 in. Plugging the 0 in, we get 0 to the 5th. Now be careful here. Remember, we are subtracting. Subtracting a negative makes it a positive 0 squared. And then we can evaluate this probably on a calculator, but we're going to test my mental math here today. 2 to the 5th, I think, is 32. 2 squared is 4. 0 to the 5th and 0 squared are 0. So I think we end up with 28 for a final answer. And what that tells us is the area under this curve between 0 and 2 is exactly 28 square inches. That's what the fundamental theorem of calculus is helping us to find. So hopefully that's the one you were looking for. That's the one my textbook calls part 2. But just in case your textbook flops them from my textbook, let's do the other half of the fundamental theorem of calculus, which I think is the most powerful one. And it looks at the idea that the derivative and the antiderivative, or the integral, are inverse operations. This is really a key concept that brings all of calculus together. So we'll do 2 problems because these are really quick. The idea is if I take the derivative of the integral from 0 to x of some function, maybe it's the sine of e to the x, or e to the t. Let's do a different variable, dt. The idea is we don't have to know how to actually find this antiderivative because we know that derivatives and antiderivatives are inverse operations. They're going to do the opposite thing from each other. So it's kind of like saying, what's 27 times 42 divided by 42? We don't have to actually do that math. It's just going to be 27. So the derivative of the antiderivative is just going to be this function, sine of e to the x, where we plug that top value into the function. Now there's one little thing I want to be careful of with that, and that is we still have the chain rule from your derivative chapter. So if I wanted to find the derivative of the antiderivative from 0 to the tangent of x of the square root of 1 plus t squared dt, It's not just x up here, it's actually a function, which means we're going to have to use the chain rule. So we're going to do the same thing we did up above, where we're plugging this in, but then because of the chain rule, we have to multiply by the derivative of that inside function. So we end up with the square root of 1 plus t becomes the tangent of x squared, and then we're going to multiply by the derivative of tangent. The derivative of tangent is secant squared of x. Now this one's kind of fun. I kind of picked it on purpose because of what it can do. 1 plus tangent squared, that's a trig identity. That's equal to secant squared. So we can simplify that a little bit. But then I've got the square root of secant squared. The square root of something squared is just the thing itself. So I actually end up with secant times secant squared. And so this one, kind of fun, came out to be secant cubed of x. All right, we got lots of questions coming in. I love it. This is your Che Calculus Office Hour. We are here every Tuesday at 5:15 Pacific Time, 8:15 Eastern Time to answer your questions about calculus. While we're answering our next question here from the list, why don't you also tell me where you're tuning in from? We are tuning in on several streaming platforms right now, so I really want to know who's in the room. So where are you from? What's your major? Give me some background on you. I'd love to see that as we look for our next question that we are going to go over. I see a question on let's do some limits. Specifically, let's put limits in the context of those indeterminate rules. So, for example, if I wanted to take the limit as x goes to 0 of sine x minus x all over x squared. Now, ideally, what we're going to do with the limit is we can just plug that 0 in. The problem is, what happens when we plug 0 in? Sine of 0 is 0. Minus 0 divided by 0 squared is 0. This ends up being 0 divided by 0. And the problem with 0 divided by 0 is anything divided by itself is 1, right? But 0 divided by anything is 0. But we can't divide by 0. All sorts of problems with this setup. It's called an indeterminate form because it really depends on what these functions are doing and how they divide to each other. It could pretty much be anything. It could be 0, it could be infinity, it could be anything in between, it could be a negative. And so we've got this wonderful mathematician called L'Hopital who actually didn't come up with the theorem. He bought it off of Bernoulli and published it as his own. But that's a whole other story. L'Hopital's rule tells us that we can take the derivative of the top that's going to 0 and the bottom that's going to 0. I usually just do a big L to say I'm L'Hopitaling. And that limit is going to still have the same value. I don't like that color green. I'm going to go with this pink color. So we're going to take the limit as x goes to 0. The derivative of sine x is cosine x. Minus the derivative of x is 1 over the derivative of x squared is 2x. The goal, the hope is that after making this change, we're going to end up with something that we can actually take the 0 and plug it into the function. Well, look what happens when we do. Cosine of 0, trig test. What is the cosine of 0? Do you remember? Cosine of 0 is 1. Minus 1. Over 2 times 0 is 0. Well, 1 minus 1 is 0, and we are right back where we started with 0 over 0, which is still problematic. So we do it again. L'Hopital's rule still works because we have that 0 over 0 relationship. So we're going to take the derivative of the numerator. The derivative of cosine is negative sine. The derivative of 1 is 0. Over the derivative of 2x is 2. And now, finally, when we plug a number in, plug 0 in this function, we'll get something we can actually evaluate and figure out the limit. Plugging in 0, we get negative sine of 0 over 2. But you remember the sine of 0 is 0. And so this limit actually does go to 0. So L'Hopital's rule is a really fun thing we can do with limits. A lot of great things there. Checking the chat here to see what other questions are coming in. Remember, we are here to answer your questions. We want to look at infinite limits without a graph. That's kind of tangentially, did you see the pun I did there? Tangent to this topic. That's kind of related to this topic. So let's look at limits, infinite limits without a graph. I'm going to do 3 quick examples to kind of show what's going on here. Let's take the limit as x goes to, these are going to be fun to make up on the fly. Let's go, we're doing infinity, right? Limit as x goes to infinity. X is going to get huge. Of 5x squared minus 7x plus 1 over 10x squared plus 4x minus 3. The thing about x going to infinity is it really allows the top dog, the biggest, most powerful term, to take over everything, and everything else gets ignored. In other words, if I take a really big number and I square it, it's going to be really big. That plus 1, that's not going to make much of a difference. When you're talking about the difference between a trillion and 1, it's just big. So the plus 1 becomes pretty insignificant and doesn't really impact things. Same thing actually happens with the 7x, because if x is a trillion, 7 times a trillion is 7 trillion. But if we square a trillion, we get a trillion, which is just mind-boggling huge. This 5x squared, the largest exponent, takes over on the fraction. Same thing in the denominator. The x squared, the highest exponent, takes over on that part of the fraction. Everything else pretty much isn't going to make a difference when we're talking about huge numbers, which means all I have to do really is reduce this huge part. 5x squared over 10x squared, the x squareds reduce out, and 5/10 reduces to 1/2. And so there is a horizontal asymptote on this graph at 1/2. It's going to get closer and closer to that 1/2, depending on what side it's coming from. Contrast that, I told you there were going to be 3 cases. Contrast that with the limit as x goes to infinity of 5x squared minus 7x plus 1 over maybe 10x cubed plus 4x minus 2. This time, the 5x squared takes over, the 10x cubed takes over. But notice when we reduce these, we end up with an x left over in the denominator. We end up with 1 over 2x. And then when we take the limit as x gets huge, this denominator is going to be huge. So we're going to take 1 divided by something huge. Well, if I take 1, if I have $1 and I'm going to share it with every single person in the world, pretty much everybody's getting nothing. Sorry. So it comes out to 0 as it goes to infinity. And that means the horizontal asymptote this time is actually the x-axis. It's going to go down to the x-axis. The other case is when the numerator takes over. If the numerator takes over and the bigger exponent's in the numerator, then it's going to go to infinity. So that's kind of how I would approach those, is you're looking at who's taking over, who's growing the fastest on these limits. So let's do another problem. But before I do, those of you that are just logging in, welcome. This is Cheg's live office hour, focusing on calculus today, answering your questions about calculus. So I'm really excited to see what questions you have. Stick them in the comments. We're going to try to answer as many of them as we can. And I've got quite a few comments coming in. Partial differentiation would be kind of a fun one to take a look at. Do you want to take a look at partial derivatives? The idea of a partial derivative is we're now working in a 3-dimensional space. And so we're going to look at how a variable is changing in one direction, not multiple directions. So let's say I've got an equation that z is equal to e to the xy plus x squared y cubed minus the natural log of y. So the idea of a partial derivative is we're going to treat the other variable like it's a constant. So if I want to take the partial derivative of z with respect to x. That funky looking d, that tells us we're doing a partial derivative, not a traditional derivative. So we're not going to confuse it with like implicit differentiation. Should be another fun topic. If you want to see implicit differentiation, stick it in the comments. We'll take a look at that. But if I'm taking the partial derivative with respect to x, that means the only variable is the x. I'm going to treat all the y's like they're a number. So when we've got e to some stuff, its derivative is e to that stuff. Chain rule then says I multiply by the derivative of that stuff. And if I have a constant times x, just like the derivative of 5x is 5, the derivative of yx is y. Plus, all right, here the y cubed, that's a constant. Nothing's going to change on the y cubed. But the x squared, that one we'll take the derivative of because we're going with respect to x. The derivative of x squared is 2x. What about the natural log of y? There's no x's in here. This is just the natural log of y. And remember, y is a constant, which means this whole thing is a constant. The derivative of a constant, did you guess it? It's 0. So plus 0, we don't really have to write it. So we could say the partial derivative of z with respect to x is this function. This function tells us how fast the function is changing in the x direction. What if I want to know about the y direction? How fast things are changing in the y direction? That's going to be the partial derivative of z with respect to y, I said. Y. Well, now if I'm doing the partial derivative with respect to y, y is my variable. X is a constant. So now the y's are the variables. So when we've got e to the stuff, its derivative is e to the stuff times the derivative of the stuff. The derivative of x times y with respect to y is just the x because y's derivative is 1. Plus x squared, that's a constant. It stays along for the ride as we take the derivative of y cubed. Y cubed's derivative is 3y squared. Minus, this time, as we do the derivative of the natural log of y, this time y is a variable. So the derivative of natural log becomes 1 over y, and that becomes a function that describes how fast things are changing in the y direction. Excellent. A lot of great questions coming in. I see a question about series. We haven't talked about series yet, so let's do a few series problems. For those of you that are just logging in, though, welcome to Cheg's live office hour on calculus. We are here every week, every Tuesday at 5:15 Pacific time, 8:15 Eastern time to answer your questions about calculus. So mark your calendars. Make sure you're joining us every week as the semester goes on. I'm excited to do some of these problems with you. And one such problem that we get to look at are series. Let's do the sum as n goes from 1 to infinity. And we want to just see if this series converges or diverges. Let's take a look at 1 over 2n factorial. There are lots of tests that we do to verify if a series converges or diverges. One of the most common ones we use is the ratio test. The ratio test is really nice to use whenever we have a factorial, because the ratio test will get rid of the factorial for us so that we can decide if it converges or diverges. So we've got this variable rho. It's kind of like a funny looking p, but it's rho is what we call it. It's a Greek letter. Rho is equal to the limit as n goes to infinity of the current term divided by the next term. So the current term is 1 over 2n factorial, dividing by the next term, which is 1 over 2 times n plus 1 factorial. Notice the n got replaced with n plus 1 in parentheses. We don't just do a plus 1 outside because that 2 is going to have to distribute. So when we simplify this, we end up with the limit as n goes to infinity of 1 over 2n factorial. Since this is dividing by a fraction, I'm going to multiply by the reciprocal and say times, this is 2n plus 2 factorial over 1. Okay. Let's go. I'll go with black for my next color. I'm going to come over here, get a little bit more space. How we handle these factorials is these factorials are going to count down. 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n. Just like 5 factorial is 5 times 4 times 3 times 2 times 1. So we've now got the limit as n goes to infinity of 1 over 2n factorial times, there's a 2n plus 2. Counting down would be 2n plus 1. And counting down would be 2n factorial. And the reason I'm going to stop here is this 2n matches that 2n. That's going to allow us to do some reducing because the 2n plus 1 or the 2n factorials are gone. And now I've just got the limit as n goes to infinity of 2n plus 2 times 2n plus 1. Everything else is gone. And we can see this, as n gets huge, is also going to get huge. If that also gets huge, it's going to infinity. The rule that we're looking for with rho is if rho is less than 1, the series will converge. If rho is bigger than 1, the series will diverge. This one is much bigger than 1, so I'm going to say it diverges. That is the ratio test, one of the most important, often used ones, especially when we get to working with power series and trying to find the interval of convergence. We'll use the ratio test quite a bit. But there are actually lots of tests that we can use as we're working with series. Another common test that we use is the integral test. So the integral test is nice whenever there's something that we can easily take the integral of. For example, if I want the sum as n goes from 1 to infinity of the natural log of n over n, you might notice that we can actually take the antiderivative of this function quite nicely because the derivative of natural log is 1 over n sitting right in that function. So we're going to go from 1 to infinity. It's just a u substitution problem where u is the natural log of n and du is 1 over n dn, which means now we're integrating from, we have to plug these in when we make the substitutions. So the natural log of 1 is 0. The natural log of infinity is infinity. And technically, we don't actually integrate at infinity. We're going to take the limit as the function goes to infinity. But the natural log of n, that becomes a u. The 1 over n dn all becomes the du. And this is an easy integral. It's u squared times a half. We're going to integrate that from 0 to infinity. But you can see really quickly, when we plug infinity into this one, it's going to become huge. Infinity squared divided by 2 is infinity. So this integral diverges, which means the series will always do the same thing. It also diverges. So there are lots of integral or lots of series tests that you kind of need to keep an eye on the series chapter. It kind of feels overwhelming, the number of tests that you have to keep track of. We've got alternating series, we've got comparison, we've got limit comparison, lots of things to keep track of. The key to success there is practicing lots of problems. So practice, practice, practice is my advice with series, and get those questions answered. Excellent. Let's find another question. Can you explain the concept of factorial? We kind of did that with the last problem. The idea of factorial is it just counts down as we're multiplying. So 5 factorial is 5 times 4 times 3 times 2 times 1. Counting down to 1 comes out to be 120, I think. Excellent. see a question from TikTok at Adam, wanted to just know about integrals, which I think gives me free reign to put any integral up on the board I want. So let's do an integral for Adam. I see a couple questions around fundamental theorem of calculus 2, probably because that's where the AP classes are right now. So let's take a moment to take a look at another integral. Let's do the integral. We'll go from 0 to 1 of e to the x over e to the x plus 1 dx. This is a good AP calculus type problem, just to really make sure you understand how the formulas work, how to plug the numbers in. With a problem like this, when we're integrating, one of the first things that I always look for is, can I make a u substitution where the derivative of part of the function is hanging out multiplied in the function? Notice if I take this bottom part and I call that my u is e to the x plus 1. Its derivative, the derivative of u, is just e to the x times the dx. Notice that is sitting right in the problem as well. So I'm ready to make this substitution to convert it from x's to u's. And as we do that, especially if we have limits, we're going to also convert these numbers, these limits of integration at the same time. So I'm going to plug 0 in here. E to the 0 is 1, plus 1 is 2. If I plug 1 in here, e to the first power is just e. E plus 1 becomes my upper limit. It's kind of a weird looking limit, but remember, e is a constant, just like pi. It's not a problem. We can handle that. Then, looking at the problem, it was a fraction. The e to the x dx, all that became my du. And the e to the x plus 1, that all became my u. And we know the antiderivative of 1 over u is the natural log of that u. And then we just have to integrate that from 2 to e plus 1. That just means, this is that fundamental theorem of calculus that you're working on right now in your AP classes. That means we're going to take this e plus 1 and plug it in here. So we have the natural log of e plus 1. And then we subtract what we get when we plug the lower limit into the function, the natural log of 2. Now, if you're taking the AP calculus test, I would stop right there. This is a safe stop because the AP calculus test does not require you to simplify your answers. So you can stop there. Don't put it in your calculator, because if you push the wrong button on your calculator, you're going to miss it. I don't want you to miss it. Safe stop, stop there. They'll give you full credit for that problem. Excellent. So welcome, by the way, those of you that are rolling in right now, this is Cheg's live office hour. I'm here to answer your questions. So tell me what questions you have about calculus. Are you working with u substitution? Are you working with L'Hopital's rule? Do you want to see some optimization problems? What are you working on right now in your calculus class that we can help you solve? This hour is yours. We are here, by the way, if you're in calculus, mark your calendars. We are here every Tuesday at 5:15 Pacific time, 8:15 Eastern time to answer your questions. So drop them in the chat. And, oh, I see a challenging integral substitution problem coming in. Let's see if we can solve that one. Let's do, it's the integral of sine times cosine. I hope you're not giving me one of those ugly ones just to watch me struggle. But we can actually solve this, right? Over 1 plus sine squared dx. Integral, not derivative, right? Yeah, it's a substitution problem. Yeah, this is a great problem because it's perfectly set up for us to do a u substitution. We need to decide, is there some piece of this function whose derivative is just resting there waiting to become my du? Notice that if u is my sine of x, just the sine of x, we'll worry about the rest of it later. if u is just the sine of x, du, its derivative is cosine of x dx. Notice we've got cosine x dx just sitting in the problem, begging us to make it the du. Now we're just going to change each of these signs into a u. So now the integral becomes the sine of x, which is u, over, get my color coding off, over 1 plus the sine of x, which is u, squared. And then the cosine x dx, all of that's going to become my du. This is something we can solve by doing another u substitution. Maybe some of you saw this from the beginning. If we had made this u sine squared of x, we could have done it in one step. But I don't usually stress or worry about making sure I do it the quickest one-step way, because I'll spend an extra 20 minutes finding the quick method when I could have solved it in 5 minutes by just starting. So just start the problem and see where we end up. What I see here is if I make this 1 plus u squared equal to my variable, and I'm not going to use u again. I don't want to get things confused. I'm going to call that a w substitution. W is 1 plus u squared. dw then is 2u du. We have the u that we want, but we don't have the 2. The nice part is what we're missing is a constant. And we can always multiply by a constant inside and outside of the radical to make things work out the way we want. So now I've got a 1/2 out front. I'm going to come over here, run that space. A 1/2 out front times the integral of 2u du. All that's going to become my dw. And so there's nothing else in the numerator. In the denominator, we have 1 plus u squared. That's going to be my w. And now we have something we know how to solve. We've got a 1/2 out front, natural log of w plus a constant. Now, we don't want w's. We made up w. That's not the answer we're looking for. So we're going to go back. W is u plus 1, or u squared plus 1. So now it's 1/2 natural log of u squared, or 1 plus u squared. It's the same thing. Plus a constant. Well, the other catch there, though, is we don't want u. U is equal to the sine of x. So we make that substitution, and we get 1/2 natural log of 1 plus sine squared of x plus c for our final solution. That was a great problem. Thanks for asking about it. Like I said, there's really a couple ways we could have gone about it. I broke it down into 2 substitutions, where first we took care of the sine and the cosine, then we took care of the 1 plus u squared. If some of you were savvy enough and saw it from the beginning, we could have made this entire 1 plus sine squared my u, and then the du would have done it in exactly 1 step. Both ways work. I'll give you a second to take a screenshot because that's such a great problem. So thank you, Ryan from TikTok, for asking that question. Thank you, all of you, for your questions coming in. These are excellent questions that we're getting. So if you haven't had a chance to ask your question yet, stick it in the chat, and we will take a look at those. I see a couple questions in the chat that are kind of related to like algebra and pre-calculus type topics. I would encourage you to join us on Wednesday evening. Wednesday evening, we're going to be doing a live as well that's going to really focus on some of those algebra and pre-calculus concepts. So mark your calendars, check Cheg's page, and we'll take a look at those as well tomorrow evening. So I had a couple questions for differential equations. Differential equations in calculus, especially AP calculus, we only really scratch the surface and do some very basic ones. Let's take a look at one such equation. Let's do dy dx. Oh, we'll call it y prime. No, we'll call it dy dx. Dy dx times x squared y to the 5th is equal to maybe x cubed y plus x cubed or x squared y. Now, this is a differential equation where we're going to try and figure out what equation y would make this whole thing true. Essentially, we've got y and y's derivative working in the same function. That's what makes it a differential equation. Y and y's derivative are related by some equation. We can actually do y's second derivative, third derivative, and fourth derivative as well, but there is a whole course you can take on differential equations that'll look at that. We're just going to look at the case of separation of variables, where we try to separate the x's and y's by getting the x's on one side and the y's on the other side. And the way we can do that is we're going to have to group these y's together on the right side by factoring out a y. So we've got dy dx of x squared y to the fifth. Oh, I hope I came up with something that's easy to solve. I might have made this harder to solve than I needed to. We'll see what happens. Factor out the y, we get x cubed plus x squared. That's not going to be too bad. I hope. We'll see. Let's see what happens. So we want all the y's over here on the left side. So I'm going to divide both sides of this function by y so that all the y's end up on the right side. Also, I'm going to divide both sides by x squared so that all the x's are over here on the right side. The other thing I'm going to do is we're going to treat dy dx, the fraction dy dx, like a fraction. And I know your calc teacher told you dy dx is not a fraction. We cannot treat it like a fraction. And then we get to differential equations, and we're going to treat it like a fraction. There's reasons that we can kind of cheat here. It's kind of some sloppy math, but really good physics. So just trust me, we can multiply both sides by dx as well. And a lot of things are moving around. Let's see what's left. The x squared reduced out. So we've got y to the fifth over y. That's y to the fourth with a dy. X squared, I'm going to distribute it onto both parts. Remember, we can't just reduce x squared unless we also do it on the other part. So x cubed over x squared is just x, plus x squared over x squared is 1. All of that is multiplied by the dx. Now that we've got all the x's on one side and all the y's on the other side, this is a differential equation that to undo the dy and the dx, we're going to use the fundamental theorem of calculus and say its inverse operation is the antiderivative. When we take the antiderivative, we end up with 1/5 y to the fifth on the left side equals 1/2 x squared plus x on the other side. We do need a plus c. It doesn't really matter which side you put the plus c on, so you can kind of choose and be kind of loosey-goosey with it if you want. But that we do need to make sure we don't forget that constant of integration. Technically, we can probably stop here. And especially if you're taking the AP Calculus exam, you definitely want to stop here because you've got your equation that relates x and y in terms of the differential equation. However, usually we consider it not completely done until we solve for y. If we can, sometimes we can't, but this time we can. I can just multiply both sides by 5. When I do, I get y to the fifth equals 5/2 x squared plus 5x plus, and we don't usually write 5c because c is a constant. A constant times 5 is still a constant, so it's plus c still. Then the only thing left to do to get this thing solved is to get rid of this fifth power, which we can do with a fifth root. And so if y is equal to the fifth root of 5/2 of x squared plus 5x plus c, this differential equation is true. Both sides will be exactly the same. And we did that using differential equations, separation of variables. Excellent. Beautiful partial fractions problem, not partial fractions problem, sorry, that is separation of variables problem. For those of you that are just joining us, this is your live office hour with Chegg to take a deep dive to help you be successful in your calculus class. So what questions do you have on your calculus classes? Stick those in the comments. We're trying to answer as many of those questions as we can with that are coming in. I saw separation of variables and differential equations come in as separate comments. That's really the same problem. But I do see a partial fractions question, which is why I mentioned it, because I was thinking about it. So let's do a partial fractions question. Yeah, let's do the integral of, let's just call it dx. Let's make it a little more interesting. At the bottom of the hour, we did a kind of a basic one. Let's do a more interesting one. I'll even factor it for you. We'll do x minus 1 times x squared plus 1. And the reason this is more interesting is the factor x squared plus 1 can't factor anymore. So we need to be careful when we set up our a, b, and c, our separate fractions that we're going to split this up into. Yes, we can put a over the x minus 1. That's normal. But because this is an irreducible quadratic, we're going to leave it as x squared plus 1. And in the numerator, we have to account for every exponent below x squared. So we have to have a b times x to the first plus a c. So there's 3 variables we need to solve for on this problem. That's equal to the original fraction, which is 1 dx over x minus 1 times x squared plus 1. Let's clear out the fraction by multiplying by this least common denominator. When we do the x minus 1's reduce, and we get a times x squared plus 1 plus this bx plus c times the x squared plus 1's reduce out, which will leave just the x minus 1, equals everything reduces out, leaving just a 1. The frustrating thing about these is we're not going to be able to pick convenient values and quickly get to the answer. We can still pick convenient answers that can get us in the direction of the correct answer. For example, one convenient value you can see we can pick for x is if x is equal to 1, this term goes to 0. So let's look at what happens when x is equal to 1. We get 1 squared plus 1 is 2 times a. That's going to equal 1. So a is 1/2. That's the easy one. Gonna have to do a little bit more work for the other ones because there's no value I can pick that's going to make this first term go to 0. That's why it's nice we kind of already know what it's equal to. It's equal to 1/2. So now I'm going to pick just numbers that are easy to do math with. The easiest number to do math with is 0. We love 0. If x is 0, I get 0 squared plus 1 is 1. 1 times a, well, a is 1/2, is 1/2. Plus b times 0 is 0, leaving just the c. And 0 minus 1 is -1. So negative c plus 1/2 equals 1. Well, if I subtract 1/2 from both sides, negative c is 1/2, and multiply both sides by -1, c is -1/2. Not too bad. We've got a, we've got c, we still need b. Unfortunately, there's not a really nice value that we can use to get at c or at b. So we'll just pick a number. How about 2? We've got 0 and 1. Might as well pick 2. So if I do 2 squared, I get 4. I'm wondering, it'd be really convenient if I ended up with an even number over here. So instead of 2, I'm going to pick 3. It might not be as nice as I'm hoping. But if I do 3 squared, I get 9. 9 plus 1 is 10. So we have 10 times a. 10 times 1/2 is 5. Plus bx, which is 3 times b, plus c, which is -1/2. So I'm still going to have that fraction. Times 3 minus 1 is 2, equals 1. Well, that's actually kind of nice because when I distribute the 2 through, that's going to get rid of the 1/2. We have 5 plus 3b minus 1 equals 1. 5 minus 1 is 4. Subtract 4 from both sides, and I get -3. How nice is that? B is just -1. Well, that is beautiful. It never works out that nice when I make up problems. What this is going to allow us to do now, though, is we can take this fraction and we can break it up into 2 fractions that are hopefully easier to integrate. So this is equal to the integral of a, which is 1/2, over x minus 1, plus b, which is -1, times x, plus c, which is -1/2, over x squared plus 1 dx. And I'm going to have to go off screen because I'm left-handed, but I'm still here, I promise. I'm going to take this fraction, actually, and I'm going to split it up into 2 completely separate pieces. Let's change colors. We're going to take this denominator, and I'm going to divide it by both parts separately. So now my problem is the integral of 1/2 over x minus 1, plus we've got a -x over x squared plus 1, plus we've got a -1/2 over x squared plus 1 dx. And I think I'm just on the edge of the screen. I swear I'm still here, solving your calculus problems. We can take the antiderivative of each one of these individually. I'm going to try and stand over here, see if this works. It's kind of hard to write like this. No, it's not going to work. This first term, its antiderivative is 1/2 natural log of the x minus 1. I'm going to pull that negative out front and say minus. You can kind of use a reverse chain rule on this problem. I feel weird being off the camera. We can kind of use a reverse chain rule on this problem where we know the x squared is going to create that -x. So we need a 1/2 times the natural log of x squared plus 1. If you can't see that in one step, don't hesitate to just use a u substitution here to evaluate this integral. But you can see when we take the derivative of this, we get 1 over this stuff times 2x, and then the 2's reduce out, and that takes us back to this. Minus, we've got a 1/2, and then the x squared plus 1, we should recognize that is the tangent inverse of x. And so that beautiful thing, that was quite the partial fractions problem that we got to attack. Should I come down here so I'm not blocking it? If you want to take a screenshot, I'll step off the camera. Did I make a mistake? 6b? I don't think it's 6b. I don't know where you're seeing the 6b. We wanted, we were looking at x being equal to 3. So it's going to be 3 times x. So we got 3, or 3 times b. So we got 3b there. Oh, you're talking about right here. Oh, you're so right. At K from TikTok, you're 100% right. That I didn't do 2 times 3 here. Good catch, good catch. How's that going to change my life? 6b, 6b. So b is -1/2. Oh, b was right here at -1/2. Fortunately, that's just a constant. So we're going to multiply by another half there. And that made it 1/4. So good catch on that. Thank you, at K from TikTok, catching that mistake for us. Trig substitution came in as a question. I think we have just enough time to do one more question. If we didn't get to your question today, we will be here next week at 5:15 Pacific time, 8:15 Eastern time to do an hour of calculus questions with you. So mark your calendars, make sure you come back. And then if you do come back, let us know you're coming back. But let's see if we can do a trig substitution problem using secant. Let's see. Does my trig substitution problem that I made up use secant? Nope, I prepared one with sine and I prepared one with tangent. I did not prepare one with secant. So are we brave enough to try and make up one? Let's see what happens. Hopefully this doesn't get too ugly. We're just going to do the integral of dx over the square root of 9. Nope, let's do x squared minus 9. Let's make it a little more interesting. Let's multiply by an x out front. Just didn't want it to be able to be solved by u substitution. Excellent. Well, the reason this is a secant substitution is when we have a perfect square minus a perfect square, it's either going to be sine or secant. We use secant when the x squared comes first. So that's going to become secant of theta, and dx, its derivative, is secant tangent d theta. So we need to make this substitution, replacing the dx with secant tangent d theta all over x, which is secant, times the square root. Oh, you boy, I missed the 9. Yeah, we need to put the square root of 9 in here. The square root of 9 is 3. So there should be a 3 in there, which means there's a 3 here. Don't you hate it when your teacher does that to you? They change the problem halfway, and then I'm going to do that to you right now. So I apologize profusely for doing exactly what I know is annoying. Okay, now we've got x squared, which is going to be 9 secant squared minus 9. The reason we do the secant is this square root should simplify very nicely. Because if I factor out the 9, I have secant squared theta minus 1. But secant squared minus 9, we should recognize, is tangent squared of theta. And that's still under the square root, but I can actually take that square root. The square root of minus 3, the square root of tangent squared is tangent. So this radical simplified down to 3 tangent. Let me write out what we have, because there's a lot of moving pieces here. We've got a 3 secant theta, tangent theta, d theta. We've got the 3 secant thetas. And then this square root simplified to 3 tangent theta. And look how much reducing we can do. That's almost beautiful. The 3's are gone. The tangents are gone. The secants are gone. We've just got the integral of 1 over 3 d theta. How simple, how perfect. That's just 1/3 theta plus a constant. Now, we did not want to have thetas in our final answer, though. We have to transition back. And so to do that, we go back to our x equals equation. If I divide both sides by 3, x over 3 is equal to the secant of theta. Normally, we would draw a triangle from here. And so just for practice, I'll draw the triangle. We don't actually need the triangle on this problem. Secant is the reciprocal of cosine. So secant is going to be hypotenuse over adjacent. So x is the hypotenuse, 3 is the adjacent, and then I can use the Pythagorean theorem to solve for the other side. It becomes x squared minus 9. But since we just have theta, we can call this secant inverse. So we've got 1/3 secant inverse of x over 3. Taking the secant inverse of both sides, theta is the secant inverse of x over 3 plus a constant. That's going to be our solution using that secant trig substitution. So that was a good one. You can take a picture of it, a screenshot of it, but we are just about out of time. So before I wrap up, I want to give a huge thank you to all of you for joining us today. This has been a lot of fun. Your questions and engagement has been great, and it's been such a pleasure to share my passion and love for calculus with you. If you can't tell by my page at Wallace STEM, calculus is my favorite topic in all of mathematics. So I love to play with it. I hope I made calculus a little bit more fun for you to enjoy and learn along the way, and I appreciate your time. Before you go, though, make sure you check out Chegg.com if you haven't already, because Chegg is here to support you 24/7 with all of your toughest subjects, with lives just like this. We're here also every Tuesday at 5:15 Pacific time, 8:15 Eastern time to answer your calculus questions. If you have trig questions or algebra questions, we'll be here on Wednesday nights as well, so check those out. Make sure you're following Chegg here on TikTok, Instagram, YouTube, Twitch for more learning content like this. Remember, I want to see you next week. Next week, Tuesday, 5:15 Pacific time, 8:15 Eastern time. Happy studying, everybody. I wish you the best of luck on your upcoming exams and your courses, and I look forward to seeing you next time. Scan that QR code and learn more about what Chegg has with our live office hours